Hi, hope you all are doing well. So, today I'm going to discuss about circulating current control and model predictive control based modular multi-level converter. So, in this discussion, I will show you the theory regarding the circulating current control, and I will also show you the demonstration of the model that how the circulating current is basically controlled. I will also discuss in detail about the control structure of circulating current. All right, so these are the agendas that in this presentation I'm going to discuss. First of all, I will briefly discuss about the MMC and in its circulating current, that from where the circulating current generates inside an MMC, and I will also discuss about the circulating current reference. What is that? I will then move on towards you know the MPC based circulating current uh, control structure. I will discuss you about the different terminologies that are related with the circulating current control via MPC, and what is the cost penalty and weight tuning and all that I will explain in this presentation. So first of all, when we have a MMC system, so in that MMC system, such as in three-phase MMC, we have the AC currents as well as the DC currents inside that are flowing inside our MMC converter. So what happens that basically, if that the circulating current is not suppressed, so it will basically results in the losses, and you will also need to size your switches, size your thyristors or power switches basically according to that. So this should be suppressed. Generally, we use inductor in order to suppress this current, but the inductor is not only responsible for the suppression of this circulating current. So for that, we need to apply some external control in our control, overall control that should uh, suppress these circulating currents. So how we can define the circulating current? It is basically, the circulating current is basically the sum of the upper arm current and the lower arm current divided by 2, and it flows internally between the arms without appearing at the AC terminal. So this is one of the main issue, that it flows internally between the arms and without it do not appear at the AC terminal. So in HVDC, it carries the DC component equal to the IDC by 3 per phase. Why is it harmful uncontrolled? If the circulating current is left uncontrolled, it contains basically the second harmonic components that increase the RMS arm currents, raise conduction losses, and stress submodule capacitors, and destabilize capacitor voltage balancing, and or degrading the HVDC efficiency. So it is very important to control the circulating current. What is our objective? Our objective is basically to force the circulating current to track the I circulating reference, which is equal to the IDC by 3. So the DC component, the DC current that we are supplying should equally divide inside the arms, right? And we need to suppress the unwanted second harmonic while maintaining the necessary DC current flow for the power transfer. So in this model, this is achieved via MPC. MPC achieve this predictably within one control step. All right. So this is our circulating current reference, which is the IDC by 3, and we have a three-phase current sharing. So in a three-phase MMC, total DC current is split equally among the three-phase legs, and each phase carry exactly IDC by 3 as the circulating current to ensure the balanced DC power flow. So it is very necessary. Uh, Plus, the physical necessity is that the circulating current is not parasitic. It is the physical mechanism by which the DC power is transferred through each MMC phase. So setting I circulating ref equal to 0 would block the DC power flow entirely, right? So, all right. Uh, so this is the time when the circulating current is enabled. Setting the ramp is 50 milliseconds, right? We are not directly enabling it, but we are enabling it through the ramp. So initially the phase 0, the circulating current is disabled, then phase 1. So linear ramp is enabled and with a 50 millisecond time period, and the phase 2, the full circulating current is active, and it suppresses the circulating current. All right. Then we have the terminology or the method, predictive circulating current control model. We have the predictive upper arm current. This is already discussed in the previous lecture. Then we have to predict the lower arm current, then compute the predictive circulating current. So the these are necessary in order to calculate the circulating current. Upper arm current, lower arm current, then we need to predict the circulating current. All right. So this is the cost penalty in the MPC. So the current penalty is equal to the IRF minus IL predictive square of this. This is the AC tracking. The circulating current penalty is this, and the switching penalty is this, and the capacitor penalty is this. Overall, the sum penalty is this, voltage sum penalty. So we have different lambdas in this cost function, and we need to calculate those as well. So we have lambda I, which is the AC current tracking. We have the circulating current lambda. We have the switching lambda. We have the capacitor lambda, and we have the sum lambda. So these are the weights that are used inside the uh, this circulating current control. So this is the overall hierarchy or the decision flow of the circulating current. So what happens is your new iteration starts. So the new MPC iteration starts, and time IU, IL, VCU, VCL, and IDC are taken. Then the current reference is set to the IDC by 3. So this is the total DC current divided among three phase. Then we need to compute the circulating current gain. If the time is less than 0, uh, the ramp is not enabled, then the ramp is enabled after the set time. And for each upper arm and lower arm candidate, it predicts the IU predict IL predictive. These are the upper arm predictive current and the lower arm predictive current. So this helps predicting the circulating current control inside and complete phase. Then select the optimum NL enablement with the minimum cost. Right. So let me show you. Yeah, here. So our circulating current is enabling at 0.1. Yeah, 0.1. So let me run the model and show you that how the you know control is happening. So this is our MMC output voltage of the MMC, and this is the circulating current. So after 0.01, it is enabled, but there is a ramp, you can see. So after the ramp, the circulating current is fully controlled and within the limits. You can see that, right? You can also see the grid voltage here. This is the grid voltage, 3 point something kV, right? So in this model, we are using a detailed model with the four submodules. You can increase the submodules according to your requirements. So this is all about the presentation. Yes, so these results are added. So in summary, this is the reference current, and it should be controlled. Circulating current should be controlled, and different gains are shown and discussed, and overall control hierarchy of the circulating current control is discussed in this presentation. Thank you.